Good morning. Welcome to Krishna's classroom. In this talk, we look at the structure of the dual space of LP mu. LP mu is a specific normal linear space. We shall describe what it is. And we are asking the question, conceptually, you can talk about the dual of that in an abstract way. As the space of all bounded linear functions on that space. But what we are looking at is, does it have a specific manifestation? And it is really fascinating that it manifests as another LP. Not the same P, but what you call LQ. Now, this is the most fascinating thing. So, we shall just develop this result and give the preliminaries of that, and then state the theorem, and then probably do some part of it today, because it's a longish proof, and we will look at that. So let us start with the details. So let X be a measure space. We will put some more restrictions on this later, the theorem, but at that moment it is. Now you see that LP mu defined as a set of all F complex value on X and such that integral finite for 1 and L infinity mu define this as a set of all F complex value of course measurable. We are only talking about measurable functions. Measurable on X, complex value, measurable on X, and such that essential supremum of on X is finite. So what you call essentially bounded functions. Okay. Now these are the two classes that you have. One of course corresponding to less than infinity, the other one equal to infinity, and together we shall write infinity. So this is a specific space on which we are going to work. Now you know that prime designate the dual space of that is the vector space of all bounded linear functions on this is the dual space. Now LP is so the question that we ask at this stage is now this is an abstract statement, all bounded linear functionals on A is a vector space. Is a vector space over the same field. Does it have any concrete manifestation? This is the question that we are asking. Now, one of the results that gives some insight into what is going on is this. Let complex valued define measurable on X then we have the famous or rather celebrated Boulders inequality. We have the celebrated Boulders inequality. given by integral less than or equal to q where equal to 1 less than n. And for p equal to infinity, some k times, or rather you can write essential supremum of right? Okay, and of course so these inequalities are okay. Now these are the three inequalities which gives some insight into what is going on. So let us see what it is. So henceforth let us write and over x. So these are the two notations. We shall use this, more convenient to write rather than this integral. Okay. Now observe that LP, LP mu, and LQ mu, where Q is the exponential conjugate of that is 1 by P plus 1. Okay. Phi of f defined as integral defines a linear function It is also a bounded by Holder's inequality. It is a bounded linear function. Bounded linear function. Thus, a bounded linear function is defined by thus every G defines a bounded linear function on LPB, where on GQ is equal to 1, and the bound is by norm G. Now this is the situation. Every G defines a bounded linear functional. Every G on LQ defines a bounded linear functional on LP. Okay, that is every the dual space of or we have this the following result. So this is an observation. It comes essentially a consequence of the holders duality. Okay. So you see that there is at least some elements of LP mu prime has a concrete manifestation as an element of LQ mu. That's a fascinating fact. So we ask the next question. If this does not hold for then at least in which cases it is true. This is the central problem. This is the central problem. When do you have equality here? For what values of En? Now note that now this is the sort of exponential conjugate relationship between E and Q. To get a feeling, you see if you take P equal to 2, what happens? Then Q is equal. In particular, P equal to 2, then is of course, you know that this is a Hilbert space. This is a L2 mu is a Hilbert space with an inner product. Incidentally, these spaces are complete. Okay? That we have already seen earlier. All right. This is where G is G conjugate. So this is the scenario that it's a Hilbert space. Now all these LPs are complete, therefore and hence Barat spaces. And you have, of course, this is the Schwarz inequalities. This is inequality. Okay, so what you have here in the Holder's inequality is a generalization of the Schwarz inequality. Okay, and that essentially gives you proves that elements of LQ manifest themselves as elements in the dual space of. Now this is the result. So we are asking the question when they are actually are they equal? Okay, because we had that inequality coming LP prime contained in or LQ prime, sorry, LQ contained in LP prime. That is easy to, that comes out of easy. So our question is this: does it completely take care of the dual space? So is LQ the dual space of? In fact, you see that the measure, the abstract measure framework is such a versatile one, because you can take into its fold finite dimensional spaces and the corresponding norms, and then what you call the small LP spaces, okay, and of course the capital LP spaces. I mean with the different types of terms. So you see, it takes care of a wide variety of LP spaces. Now let us recall what we did last time. did some investigation. We have already that L infinity mu linear function surface is properly contained in. This we have proved last time. Therefore, our expectation in the extreme case equal to in fact E equal to 1, the dual contains element. L infinity. That means L infinity are they equal? In some except with some restrictions on that. With some restrictions on the measure some pathological cases. This is the equality. Okay, so this is equal. So we have to put some restrictions. Now the restrictions are in general widely true, and we will just use that. To avoid such mu is a so this is the additional assumption. Okay. Now we are well set to state the main theorem. So let us state that. So the question, we will reframe it. Is determined by a G belonging to such that equal to which is given by this is the definition. So you have all elements of LQ determines a bounded linear function for all 1 less than or equal to p less than or equal to. So we have seen that the two extreme cases are to be treated with caution. But we look at this. So we look at the following. So we make the statement in the light of that example we have looked at. Just consolidate whatever we did earlier and just make some statement. And the statement is this: for p equal to infinity, for p equal to infinity, equal to 1, L1. That is, every element of L1 mu determines a bounded linear function on L infinity. But there are bounded linear functionals, okay, on L infinity mu which does not take this form. Which do not get represented as as 5G. Where of course 5G we have defined. Okay. That means there exist linear functions which are not represented by these integrals. Okay. In the case where p equal to infinity, that is clear. That's what we have seen. So we shall examine the following. Situation. So we will now state the theorem, main theorem. Okay, let me state the theorem. Okay. Incidentally, most of the, or rather all the cases that are relevant for applications generally have these sigma finite measures. For instance, you take the Lebesgue measure. It's a sigma finite measure. So in all such cases, there are some pathological situations you can artificially construct, but they are not of much relevance when it comes to application. This is one of the sections. I belongs to LP. I for so this is the symbolic way of putting it across. there exists a unique, there are two statements here, unique G belonging to LQ mu, where Q is the exponent conjugate of P, that is now you see that when P equal to 1, you get Q equal to infinity, and vice versa. Such that the linear functional, the value of the linear functional on f is given by the integral mu LP mu, the first equation that we write. So the first part of the statement is the existence of a unique element G in LQ such that the bounded linear functional takes this particular form, that is simply writing the following. This is the statement that you have. Moreover, what is fascinating is the following, that it is also a norm preserving. By 1, then we have norm of 5. This we have defined in the last lecture. This is the second stage. Okay. That is LQ is isometrically isomorphic to under the stated conditions. So we prove something remarkable. Okay. What we prove is this: for this whole class, the dual manifests as a beautiful structural theorem. Gives a lot of insight. It's a wonderful theorem. Okay. Very powerful. So you can accept the integral form. It's readily available. So all computations you are enabled by this concrete form of the given linear function, and that's important because we now have a very concrete form for the linear functional, and you can. There will be many places where computations would arise, and in all those situations, we can, with no hesitation, we can assume that the linear functional is manifest as the integral idea. And that's the strength of this particular theorem. See, this is the most beautiful statement. And not only that, it has also the property that it's now preserved. That's why you have an isometric isomorphism. We'll partly look at, because the proof is rather longish. So we just dispose of some of the simple things and then leave in the future talks, or leave for future talks the actual proof, the detailed. So what are the questions that we have? So let us, before we take up the proof, we have the following statements. I mean, the conditions are given in the theorem. The questions that we have to solve are: 1. Existence of so this is the existence of 2. Uniqueness of such a G. That means there exists a unique G in LQ with the stated properties. And third one is, of course, the norm-preserving structure. Norm of So these are the 3 things that we have to explore. Some of the simple things let us explore first. Okay. Some part we have already explored, namely that the bound for phi is given by. Okay. So what are things we have? Existence, of course, the question. This is to prove Now uniqueness to be proved. Uniqueness to be proved. Then the equality in 3. Equality this is to be proved. But what we have is less than or equal to if such a Q exists. Now this is the immediate consequence of the Holder's inequality. That's why Holder's inequality is very important. Contains a lot of. It gives some insight into the geometric structure of the space. Okay. It will be nice in this context for you to look at R2 with LP now and look at the shape of the unit balls. Now you see that, or the unit circle, or the unit disk. You see that the unit disk has a perfect symmetry only for the case p equal to 2. Okay. In all other cases, they have different shapes. But this is very, very interesting. The sort of shapes that come about. Now, that's very interesting. That's what I said. This LP structure gives it the right kind of gives the right kind of geometry. Second aspect is that, because in finite dimensional spaces, the set of all elements in LP and LQ are the same. Okay. So they are finite dimensions. In all finite dimensional spaces, it is so. But the moment you go to infinite dimensional spaces like LP, this is to be correct. As I have said yesterday, you take L1 and L2. Okay, every element of L1, you see that it is in L2. Okay. Oh, sorry. Is it that way? Yeah, not the other way. Every element of L2 is in. That is easy to. When you see that, this we have small. If you look at the sequence 1 by n, the sequence 1 by n, if you take the norm, L1 norm of that, then it is going to be sigma 1 by n. Sigma 1 by n is not convergent, so it is not there in L. But if you take the norm of that, the L2 norm of that, then it is going to be sigma 1 by n square. That is convergent. Therefore, it's an element of L. Okay. So this is we'll just keep that particular example in mind. So all LPs are different from LQ. There is a sort of relationship between them and depends on the space how this inequality is. That means. Okay. Right. Now we will just prove one or two little things, and then where it is simple to prove, and then postpone the proof of the main result. That means proving the existence, and that's a difficult part. Often it's a difficult part to prove the existence of G. When you have seen that given a G in LQ, LP, phi F is, or phi G is essentially a bounded linear function that we have seen. So we are now trying to work out the converse. The converse is always one way. It will be very easy in these kind of research, because what happens is that, and that actually gives the insight into asking a question whether there is equality or not. Okay, so let me just take up the proof. So we proved two. Actually, the second statement, that is easy. Linkers. That's easy to do. That is, G is unique such that this is the statement. So we assume the existence. We are making a qualified statement that if it exists, then it is true. So let us work on. Okay. Suppose G and G prime satisfy one. That is, G prime D. Then what you have is, this is for every F belonging to. Then what we have is this. LP mu. And in fact, integral over x, suppose you take f to be chi e. Finite measure equal to 0. Chi, then this is equal to 0. That is, f is equal to 1 on E. F is equal to 1 on E, and outside it is 0, and it is certainly an LP element. Okay. What does this imply? This implies integral on G of g minus g prime, that is integral over E 0 implies almost everywhere on. So it is almost everywhere. It is g minus g prime equal to 0 on E. So within in the context of the measure mu on E, g equal to g. This is the implication of that. Now mu is a sigma finite measure. This means what? You have n measurable sets. Finite. That's the meaning of that. Now g minus g prime equal to 0 almost everywhere on each En. So they're all sets of finite measure. Okay. Which implies g equal to g prime or we shall simply say that g is equal to g prime in the context of the measure. So that equality is now proved, or the uniqueness is proved. That is, G is unique. Unique with respect to mu. I put this bracket that in the context of mu. So we have proved the second part, namely uniqueness, because that is very simple to prove. We took it up immediately. So if G, such a G exists, then it is unique. Now comes the next thing. Take up the special case where now clearly by Holder's inequality, norm of phi Q. So we shall observe that if phi is equal to 0, that means it vanishes at every point of LP. So that is the existence of that. When G equal to 0. So that is rather trivial. And you see that all the both is then so all the theorem holds good when phi is 0. So we shall assume that. Phi is not equal to 0 or so shall assume that norm of phi is greater than 0. That's assumption. So norm of phi equal to 0, then you have G equal to 0. So this is solution. Okay. So we shall take this up in our next lecture. There is a slightly longish proof and needs very careful consideration. So I think I will stop here. Thank you very much. Very nice. Thank you.